Alright class, in this video we're going to look at nuclear reactions and nuclear decay. If you look at the joke on the left, they're carbon dating. Two carbon atoms are going out on a date. It has to do with the half-life. You also have the joke, what did the nuclear physicists have for lunch? Fission chips. Get it? Fish and chips or fission chips. Alright, so here's a quick review of how to name nucleuses and atomic number, atomic mass, finding your protons and neutrons. The first is your mass number. That's how heavy something is. Then you also have your atomic number. That's how many protons there are. And you also have your element symbol that's located there. The X determines what symbol the name you use. The following chart shows the band of stability. That shows how stable different elements are. On the left side shows the number of protons, and they increase from left to right. The top shows the number of neutrons. Remember, neutrons are neutrally charged, protons are positively charged, and electrons floating around the nucleus are negatively charged. We want to make sure protons and electrons have enough blocking in or neutrons in order to keep it stable. Okay? So this is a 1-to-1 ratio in red. You notice as my protons go up, I'm going to need more and more neutrons to withstand the big difference of positives and negatives. Nuclear reactions involve changes in your nucleus. That's where your protons and neutrons are. Chemical reactions involve loss, gain, and sharing of electrons. So that's the main difference between the reactions we've been seeing throughout the year and your nuclear reactions. Your different isotopes have different number of neutrons of the same element, might undergo very different nuclear reactions, even though the isotope have the same chemical characteristics. The chemical characteristics are based on the number of electrons in the valence shell. I made a review video on that in chemical bonding, which you could watch in my playlist. Alright, there are three main types of emission we're going to look at. One is called alpha emission. In alpha emission, you produce a helium atom that has 2 protons and 2 neutrons. So let's say you start with a uranium atom with 238 mass number. If I release 4 mass number, subtract 4, you get 234 for your mass number. You actually turn into a new element as well, because I started with 92 protons, I go down to 90 protons. If you look in your periodic table, that's the element thorium. This releases an amount of energy which is useful for nuclear reactions. Second type of emission is called beta emission. In beta emission, you get rid of an electron. So here I have an iodine atom. I'm going to release an electron. You notice that my atomic number will actually go up from 53 to 54. A neutron becomes a proton, and an electron is ejected. That again releases energy. Last type of emission we'll talk about is called gamma emission. In gamma emission, you start with an element, you make it in an excited state. By doing that, it can release a gamma photon. Photon is a light molecule. It actually doesn't have any mass, and it does release an enormous amount of energy. That's how the Incredible Hulk was formed. They actually got it from gamma rays shot at him. So this chart here shows the general nuclear equations. You need to know the different types of decay that's on your formula charts. Alpha is helium, beta is an electron. Electron capture and positrons are also sometimes talked about. That's where you add an extra electron there. Next we're going to talk about half-life. A half-life of an element is the time it takes for 1/2 of a sample to disappear from the solution. That's when we looked at carbon dating in the first slide. So, half-life, if you have one half-life, you're going to have 50% of your original sample. After the next half-life, you'll have half of that, or 25%, 12.5, and so on. Eventually, you'll go down to even 1 atom, and in that case, the atom will either turn into a new element or stay the same in each half-life. This picture shows a nuclear fission reaction. In fission, think about a can of soda. So let's say I have a can of soda. and it starts fizzing, the molecules will start coming out of the can. We started with a big can of soda, and now we're getting to a smaller can. In a fission reaction, we start with a big molecule, let's say uranium in this case. We add a neutron on it to make it unstable. That releases two separate elements. What's neat about this is it actually releases neutrons with it, and those neutrons could hit more uranium atoms and cause a chain reaction. This also releases an enormous amount of energy. This is how nuclear reactors work. In a nuclear reactor, you're going to take those uranium atoms, you put it in the core here. When it releases energy, it's actually going to turn the water into steam. That steam will help move a turbine. These spin around, and they spin with kinetic energy, which connects to an electric generator, and that's what heats up, makes electricity for your houses and whatnot. You also have to have the cooling tank to lower the temperature to make sure it doesn't overheat. This is essentially what Homer Simpson does when he's working. He's essentially in charge of these control rods that will move up and down to limit or increase the number of neutrons that get formed. Nuclear fusion, on the other hand, to fuse together means to make bigger. In this case, I start with two hydrogens and I make an extra neutron in that hydrogen. This is the reaction that powers the sun. Fusion reaction actually releases a lot more energy than a fission reaction because you're actually bringing together the electrons going through the atom and get new elements. Scientists are working on trying to make this reaction occur using cold fusion so they could actually contain it. That's the Spider-Man 2, remember Doc Ock, the Dr. Octagon guy? He tried to do the fusion reaction where he held it with his arms and then it broke his arms off. And that's how he turned to be a bad guy. Alright class, so this gives a basic overview of nuclear chemistry. You'll see this in the chemistry unit and the physics unit, so if you're going to take physics next year, this will be a good review as well. If you have any questions, leave a comment down below.